Our topic in this lecture is called Meaningfulness. It's a subject that's attracted some attention in the measurement literature ever since work in the 1940s of S.S. Stevens. It's a topic that has been very controversial, and it continues to be one not fully resolved. I will be reporting some results here today. There are people working in the field who are not by any means satisfied with the nature of the definition of meaningfulness that will be given here, and I think it's safe to assume that in a few years this lecture will be distinctly outdated. The problem of meaningfulness can be raised in two quite distinct ways, and then we can attempt to study how they relate to each other. One of these is fairly familiar to most people who have thought at all about measurement problems, and it arises in the following sort of way. You have got some sort of an empirical structure, and you've established that it can be mapped into some numerical structure. One realizes fairly quickly, that, however, that one must be quite careful in using the numerical structure not to invoke aspects of the number system that are not involved in the representation. A very simple example is, let us suppose I have an ordinal scale, and I have three objects, and let's call them A, B, and C. And under a particular ordinal scale, A maps into 2, B maps into 6, and C maps into 8. Now, arithmetically, we know that 2 plus 6 equals 8. Does that relationship, which qualitatively we would say that somehow A and B combine to be equivalent to C, does that relationship have any meaning? And the answer is, in the case of an ordinal scale, no, it does not have any meaning. That is, if I were to change the scale, for instance, by squaring all of the values, so A went into 4, B went into 36, and C went into 64, then the additive relationship that I had noted in the particular scale is simply violated. A similar kind of example comes, say, with temperature. If somebody says to you that yesterday's temperature was double that of today's, simply because yesterday's temperature was 40 degrees Fahrenheit and yesterday's was 20 degrees Fahrenheit, the statement is valid as long as you know that the measurement is in Fahrenheit. But as a general statement about measurement, where you're dealing with an interval scale as you are in temperature, to say that the one temperature is double that of the other is meaningless. Similarly, even with ratio scales, one has to be careful. If someone asserts that the weight of the Earth is 10 to the 5th, that is without any meaning unless I specify the units in which that statement is made. It may have then, suppose I said the units were tons, it may or may not be true that it's 10 to the 5th tons, or it's rather more than that, actually. But it has no meaning without the specification of the units. You can't ask the question whether it's true or false unless you know what the units are. At the same time, there's another notion of meaningfulness that one has to worry about that's a little more subtle. It's something that arises, for instance, in dimensional analysis. And that is, suppose I'm in the qualitative structure, and I want to talk about some relation in that qualitative structure. I can ask whether that relation has any meaning there. And now the issue becomes, what do I mean by that? Intuitively, what I would like to be saying is that the relation can be defined in terms of the relations that define the qualitative structure. And if I could give a nice, clean, formal definition of what it means for one relation to be defined in terms of other relations, then the problem of what are meaningful concepts in the qualitative structure would be easily resolved. The difficulty is that no one at the present time has a sufficiently general concept of definition to permit us to say what that sentence is, what really is intended by that sentence. And so it has been necessary to approach the problem with a certain element of indirection. One notion of well, there are really several notions of an indirect sort that we will be dealing with, which all come together under certain assumptions, but in fact are quite distinct, and this is part of the problem of the meaningfulness issue, because these different notions in the general context do not all agree. For example, one can say that a necessary condition for a relation to be meaningful is that all the transformations that leave the defining relations invariant should leave the relation in question invariant if it is definable in terms of those defining relations. This is known, and I'll come in a few moments to an exact definition of it. It's known as invariance under the endomorphisms of the structure. That's one reasonable notion of or one necessary condition of what a meaningful relation should exhibit. Another property that one might invoke is to say, well, all right, I have qualitative structure, and it maps into some numerical structure, let us suppose. And now I have another relation that I wonder whether it is meaningful within the context of the given structure. Well, if I append that relation to all of the ones we have, and if it does not change the class of homomorphisms into the real representation, then I can say that it is not adding any further constraint to the qualitative structure, which is another way of saying that it must be defined in terms of that qualitative structure. It's notions of this sort that people have attempted to use in capturing the concept of meaningfulness. I will, in a moment, begin to spell these out in some detail. There will be two areas to which these ideas are applied. One has to do with statistics. There's been a fairly major controversy in the psychological literature about how statistical constraints and measurement constraints interlock with one another, and we'll have something to say about that. And then in the second lecture on dimensional analysis, I will once again bring up the notion of meaningful relations in connection with physical laws. So now let me begin to discuss with more precision the various concepts that are involved. We can work in this discussion with quite general systems. We don't really need to specify in any detail the nature of the axiomatizations that are involved, but rather what we'll do is postulate that we're working with general relational systems, that is, a set of objects and then a series of relations that I'll number through 1 through n. These are essentially the kinds of relations that are established by axioms. For instance, for example, in an extensive structure, S1 would be the ordering relation, and there'd only be one other, namely the operation O, which is a trinary relation. I'll be talking here always about pairs of relational structures, and the major requirement will be that the corresponding relations SI and TI will be relations of the same order, and I'll use the symbol K sub I to denote that order. I will be dealing with situations where I have a homomorphic mapping from A into R, and in general, in measurement contexts, we will think of R as being a numerical structure, so R will be a subset of the reals, and T1 in general will be greater than or equal to. But much of what I have to say doesn't require that specification. I'll let capital Phi of AR denote the set of all homomorphisms of the relational structure script A into script R. That is, little phi is a member of capital Phi if and only if for all K sub I tuples of elements in A, if that K tuple is in the relation S sub I, it is in the relation S sub I if and only if the image of it is in the relation T sub I. In a typical representation theorem, then, is really the assertion that this set of homomorphisms is non-empty, that one has chosen the relational structure R to be of the right character, so there is at least one mapping from A into R. The uniqueness theorem characterizes a set G of functions from R into itself such that two homomorphisms, phi and phi prime, are two homomorphisms if and only if there is some G in little g in capital G such that phi prime is phi with then G applied to that. Those are the typical kinds of representation and uniqueness theorems we have been dealing with in this series of lectures. Now, in the case that we're dealing with mappings of the relational structure A into itself, so we'll be talking about homomorphisms from A into itself. Those homomorphisms are given the special name of endomorphism, and if an endomorphism is both one-to-one and onto, it is called an automorphism. And particularly in the lectures on non-additive concatenation structures, you will recall that automorphisms played a considerable role. Now, what I want to do at this point is, on the assumption that I'm dealing with an automorphism from script A into script R, I want to talk about relations in R and what they refer back to in the qualitative structure script A. So we let T be any relation of order K on R, and we let little phi be any homomorphism from A to R. Then I'll define the set S of phi and T. It depends both on the homomorphism and on the element on the relation T. And that'll be the set of K tuples, the elements of which are in A, such that the image of those under phi lie in the relation T. In this sketch here, you get a picture of what it's like. If this symbolically represents A crossed with itself K times, and over here this symbolically represents R crossed with itself K times, and the mapping phi is mapping from the A space into the R space. then if I have a relation in here, a k-order relation, it's a subset of this, so T is a subset of that in here, then I look back under the homomorphism to find that set of elements in here that mapped into it, and that set of elements I'm going to call S of phi T. Now we'll find that we are particularly interested in those relations in the image space, in the representation space, whose referent is independent of the homomorphism you choose. So we'll define a relation in T to exhibit A reference invariance relative to R if and only if for every pair of homomorphisms, phi and phi prime, that take script A into script R, the set of elements that map into T under phi is exactly the same as the set of elements that map under phi prime into T. And we'll call that common set S of T, suppressing the notation of the homomorphism because it doesn't depend on the homomorphism. Now, those kinds of relations seem to have a very distinctive importance because any relation of that character that I speak of in the representation space script R has a unique meaning back in the underlying space, the qualitative space script A, quite independent of which of the homomorphisms I happen to be using, so that it has an invariant meaning, and that's why it's called reference invariant. This is a concept that arose really in work of Adams and Fagot and Robinson, and was also studied at some length in Fonsogel's treatise. I will also say that a relation S in the space A, on the set A, is structure invariant if S is A reference invariant relative to A. That is, I now am looking simply at the endomorphisms of the space script A, and any relation that is invariant under those endomorphisms I will call structure invariant. And in fact, this trivial first theorem is simply the statement that structure invariance is the same thing as invariance under the actually it's under the automorphisms of no, this is incorrect. This has got to be the endomorphisms. The endomorphisms of script A. Now let me give you an example of a failure of reference invariant, the one that is fairly important and that sometimes doesn't seem to be very well understood. Consider a probability structure of the type that we spoke of in the lectures on probability. So we have a set X, an algebra of events script E, an ordering, a qualitative ordering of more probable than. And we were interested in representations of it that involved a probability measure defined on script E, such that A is more probable than B if and only if P of A is greater than or equal to P of B. Now, it's customary to define independence in the numerical structure in the following fashion. We'll say that A is independent of B if and only if P of A intersect B is in fact equal to P of A, P of B. And the question has arisen, since independence is an extremely important concept, is this notion is this notion of independence as a relation in the underlying qualitative structure. Is that a meaningful relation in that structure? That is, can it be defined in terms of the primitives of that structure? And the answer is that in general it certainly cannot be. And the reason being is that unless you have very strong requirements, there are homomorphisms from the qualitative structure into the numerical structure, that is, probability mappings, that are not identical to one another, and therefore this concept is not reference invariant. If I have a quite distinct probability measure and I look at this same product relationship that is numerical relation in the representation space, it depends on which of the homomorphisms, that is, which of the probability measures I'm using, as to what I get back in the way of a relational structure in the qualitative space. And because we know that in general there is not a unique probability representation, even with the requirement that the probability of the universal set be 1, it's not unique, that means that the concept of independence is not reference invariant, and therefore it is an independent concept that really should be added to the qualitative structure. It is not something that in general will be definable. Now, the issue that concerns one in the study of meaningfulness is whether or not a relation that is A reference invariant relative to R and the resulting induced relation in the qualitative space, whether that is an appropriate definition of meaningfulness, or, for example, whether structure invariance, which in my preliminary remarks I suggested might be a sensible definition of invariance, because what this is doing is saying that we're looking at a structure that has an invariant quality provided you only look at the transformations that don't that are invariant in the original structure that you're talking about, the script A structure. Now, if these two notions were basically the same, there'd be no problem. However, it turns out that things are not quite that simple. We also have really two concepts of structure invariance to talk about. I've written here the definition in terms of the A space, but there's another definition in the R space, structure invariance of the relation T. And so we have really three distinct concepts: structure invariance in both of the relational structure and reference invariance between them. And the real question is, which, if any of these, should be taken to be a concept of meaningfulness? However, it turns out that in many of the important situations, the concepts are all the same. And I want to show a theorem in a little bit that establishes a fairly general circumstance under which they are the same. In order to proceed in that direction, I need another slightly modified concept of an endomorphism that's given in definition 2. Supposing that P is a subset of the set R in the representation space, and denote by script R sub P the restriction of that space to P, then any homomorphism that relates script R restricted to P into R will be called a partial endomorphism with domain P. And the reason that we're interested in that concept of partial endomorphism is embodied in the second theorem. There's a slight supposition here that the notion of equality in R is reference invariant. If that is not the case, we're going to be in a lot of trouble. Things get very messy. So I'm going to assume that that is reference invariant. Then I look at two homomorphisms from the qualitative space to the representational space, and the assertion is that phi and phi prime are two homomorphisms if and only if there is a partial endomorphism gamma with domain phi sub a such that phi prime is of the form phi then with gamma applied to it, and gamma is defined just on the image of phi. So that this is essentially stating the nature of the uniqueness theorem. It's saying that under the rather weak assumption that equality is a reference invariant, then the uniqueness is characterized by the partial endomorphisms of the representational space. Under that same assumption about equality being reference invariant, we now can establish a characterization of what it means for a k-order relation in R, call it T, to be a reference invariant relative to R. And what is involved here is that we look at all the partial endomorphisms with domain phi of A and look at the elements that are in the kth product of the image of A under phi, and that element, those k-tuples, are in T if and only if the image of them under the partial endomorphism are also in T. So this is an analog, really, of Theorem 1. The Theorem 1 defines structure invariance in the underlying space in terms of the endomorphisms of A, and this defines what it means in the imaging space for a relation that's reference invariant. It has to have invariance under the partial endomorphisms. Now the next theorem is beginning to tie some connections between these concepts. We suppose we have some homomorphisms. We suppose that T is a relation in the representation space. Then the first assertion is that if T is a reference invariant relative to R, which is one of the concepts we think it's important, then the reference set, S of T, is in fact structure invariant. Now, one immediately asks the question, suppose I have a structure invariant set in the underlying space. Is that the referent of something in the image space? Then those two concepts would be really the same. But in the general situation, that's not the case. Now, I will be talking about assumptions that lead to that equivalence. If T is a subset of all the conceivable kth order images of the homomorphisms, that is, in a certain sense, what this requirement is that the representation space should not be too large. What we're going to be doing is restricting the representation space and then looking at relations in that. So if the representation space is been chosen efficiently, this condition will be met, in which case, if T is a reference invariant relative to R, it will prove to be structure invariant in R. So we're getting very close at this point to these concepts being the same. What we're doing at this point is saying that they're not quite the same because this is not an if and only if statement up here, and they're not quite the same down here unless the space well, you can view it either way, that the representation space is not too big, or that you are careful to choose your relations in that space that you're interested in so that they're only extending over the region that is being used in the homomorphic mappings. And if you do work with that restriction, then the relations that are reference invariant are also structure invariant. So from what I just said, it's clear that we need to capture in some fashion a notion of the appropriateness of the representation relational structure to the qualitative structure. That seems to be at issue here. And let me remind you of several things we know which will begin to suggest a definition of compatibility. The first thing that we know is that if alpha is an endomorphism of the qualitative structure and phi is a homomorphism from the qualitative structure to the representation structure script R, then phi applied to alpha is also a homomorphism. And secondly, what Theorem 2 said was that if we had two homomorphisms, then there is a partial endomorphism in the representation structure such that the one homomorphism is the other homomorphism with the partial endomorphism applied. Thus, in particular, if we're dealing with the homomorphism that's obtained from the endomorphism alpha with phi applied, there must be a partial endomorphism that does the same job, so that we have either we apply the endomorphism, then the homomorphism, or the homomorphism and then the partial endomorphism, and we get the same thing. I can sketch this down here. If this is the A space and this is the R space, then the endomorphism in here does that mapping of a typical point. The homomorphism then takes it here, or alternatively, we can take the homomorphism here, and then there's a partial endomorphism here. And what the assertion is that to each endomorphism alpha, there's an appropriate partial endomorphism that does the same job. Either you go alpha phi or you go phi gamma, and you get the same answer. Now, what is not true in general is the opposite statement, that beginning with a partial endomorphism, we don't know in general that we're going to have an endomorphism back in the qualitative space that does in effect the same job as the partial endomorphism. And I will take the existence of that as my definition of compatibility. I shall say that the relational structure script R is compatible with the qualitative structure script A if and only if, first of all, there is a homomorphism between them, and secondly, if I take any homomorphism and I consider all of the partial endomorphisms, then there exists for each partial endomorphism an endomorphism in the qualitative structure such that phi applied to the endomorphism is the same as the partial endomorphism applied to the homomorphism. So that this property now goes both ways, and that is the notion of compatibility. And as you will see in this Theorem 5, it appears to be the right kind of concept. I'll assume again that I do have at least one homomorphism, and I will assume that equal is A referent invariant relative to R. Let T be any relation on R, and let S be a relation on A in the qualitative space. And let us assume that R is compatible with A in the sense of the definition just given. Then there are two statements to the theorem. First, that T is A reference invariant relative to R if and only if T is structure invariant. So the concept of reference invariant of a relation and structure invariance in the representation space are the same under this assumption of compatibility and this, of course, this assumption that equality is referent invariant. The second statement is that if S is a structure invariant relation in the A space, that is true if and only if I can find a relation in the R space, call it T of S, that depends on S, such that the set that I'm sorry, I've not quite stated this right. There has to exist a referent invariant relation T of S such that the referent of T of S back in the original space is in fact the given S, so that any structure invariant relation is representable in the representation space by a referent invariant relation. This means then that the three concepts, reference invariant between the two spaces, structure invariant in the qualitative space, or structure invariance in the representation space, all of these are the same notion, provided that the compatibility holds. Now you might reasonably ask, well, when does compatibility hold? Is this a very strong assumption, or is this something that we would normally expect to obtain? And there's a corollary that gives a sufficient condition for that, that is one that we've run into fairly frequently and seems to be, for many purposes of measurement, quite satisfactory. Suppose that all of the homomorphisms from A to R in fact have a common image. Usually that would turn out to be all of the positive reals, but we don't need to be quite that specific. But they all are mapping onto the same set. If that is the case, and then under the assumptions of this theorem except for the compatibility requirement, then every endomorphism in the qualitative space is in fact an automorphism, and every endomorphism in the representation space is an automorphism there. Secondly, those two groups of automorphisms are isomorphic. And third, and the most important aspect of this, R is in fact compatible with A under that assumption. So that in most of the kinds of measurement situations that we have been working with, the compatibility requirement is satisfied, in which case these reference invariance and structure invariance concepts are all the same. And at least tentatively, several of us have come to the conclusion that this is a suitable definition of meaningfulness in this class of measurement situations where the compatibility requirement is satisfied. So we will treat relations as meaningful provided they are structure invariant in a measurement situation where the compatibility holds. The nice thing about this compatibility requirement is that it's really a very simple characterization of the uniqueness theorem of the representation. We can characterize uniqueness either in terms of the endomorphisms of the underlying structure or the partial endomorphisms of the representation structure. Either of those is equally good when the structures are compatible. Now, the two major areas in which these meaningfulness notions have played a role in measurement theory have to do with a controversy that has arisen in connection with statistics, and, as I said before, in some of the work on the theory of dimensional analysis. I will talk about the latter in the lecture on dimensional analysis, the second lecture, And I will close this lecture with a brief discussion of the statistical question. Let me take some specific examples which are relatively familiar. Let me suppose that in the representation space, I take a sample of observation which I'll call x sub I. Then the mean is defined in the standard way, the sample mean, as the sum of the values of the x sub I averaged over the number. And the sample standard deviation is also defined in the usual way. Now, in Stevens's original discussion of these matters, he took the position that certain statistics were compatible with certain measurement, types of measurement, certain levels of uniqueness. That has been, I think, slightly misunderstood because it isn't really the statistic per se that has compatibility, but rather it's the assertion in which the statistic is used that makes the difference. For example, let's consider a statement such as the sample mean is equal in value to a particular number w, which can be written as x bar minus w is 0. Now that defines a k plus 1 order relation. That is, there's a whole set of possible observations that would be consistent with that statement. And each one of those is an element of the relation that is defined by that equation. Now, if we assume that these numbers are coming out of the representation of some qualitative space, then it's not difficult to see that this relation, the relation defined by that equation, is referent invariant for both ratio and interval scales. The reason being that x bar under an interval transformation would go into alpha x bar plus beta, and w would go into alpha w plus beta. Therefore, looking at alpha x bar minus alpha w, let me write it a little more carefully. In the transformed picture, I'll have this. The betas will cancel. I can pull the alpha outside, and I get that. And this will be equal to 0 if and only if x bar minus beta is equal to 0. So the invariance will obtain under interval scale transformations. On the other hand, were I to make a slightly different statement, such as the difference between two sample means is equal to a particular number, that statement is referent invariant for ratio scales, because then I'd look at alpha x bar minus alpha y bar minus alpha w, and I can pull the alpha out, and the two statements are equal to 0, are equivalent. But it is not referent invariant under interval transformation, because I get, in that case, alpha x bar plus beta minus alpha x bar minus beta minus alpha w minus beta, which is then a plus, equal to 0. These betas cancel, but that one doesn't. And so no longer does it then turns out that you have alpha x bar minus y bar, oops, this was a y bar here, minus w plus beta is equal to 0, and that is not, when that's 0, that does not mean that that is 0. Similarly, if I look at the sample standard deviation being equal to a particular number, that's reference invariant for ratio scales, but again, it's not reference invariant for interval scales, because in the interval scale transformation, the beta will have disappeared here, but it will not have disappeared here. On the other hand, the ratio of two sample standard deviations will prove to be reference invariant for interval scales. So it's not the statistic itself that is either meaningful or not. It is the statement that it enters, the hypothesis that is being asserted, that either will exhibit the appropriate invariance or not. I think that there is only a limited amount of confusion about that point, although it sometimes has been overstated. But I think there's general consensus now that one connection between measurement and statistics is that the hypotheses one writes down should be meaningful, i.e., referent invariant statements. That if they are not meaningful from a measurement theoretical point of view, then there really is no point in proceeding further with any statistical arguments. The part of the argument that has been far more controversial concerns statistical testing and whether or not in a particular context one is free to use so-called parametric, usually Gaussian, tests, or whether one should be confined to using non-parametric tests. And let me try to describe the typical kind of situation. I think it really turns out that once you describe it carefully, then it's easy to see that there isn't really much of a controversy. So the situation that we have in mind is a qualitative structure with an ordering and some other relations, and a representing structure, which is a numerical one with the usual greater than or equal to and some other relations, and they're the same order relations. Let me also assume that I've got some subsets of A, call them B and C, and they're disjoint. And on those subsets, I have probability spaces with different algebras of events, of course, and different probability measures, P and Q. And I'll assume that these are countably additive probability spaces. Now, we'll say that a function from A into the reals is a Gaussian representation for the structure composed of the set A, its ordering, and the two probability spaces, provided it's order preserving, and provided the restriction of that function to B and C, respectively, are random variables that have Gaussian distributions. And that's the kind of assumption that one frequently sees made in statistics books, that you're dealing with a random variable that has a Gaussian distribution, but we're adding on the further requirement that the random variable be order preserving in the order of the measurement structure that's involved. One can see easily that under those assumptions, psi is in fact a homomorphism of the order part of the qualitative structure into the ordered real numbers. In general, however, psi need not be a homomorphism of the measurement structure into the reals. Maybe an example will make this very clear. Suppose that I'm concerned with reaction times. Now, we're dealing with time, which is measured in an extensive fashion. We have some qualitative way of measuring time. It leads through the measurement theory to the usual numerical representation of time, where time intervals are additive. So there's an extensive structure there. Let me suppose, probably contrary to fact, that observed reaction times have a log normal or log Gaussian distribution, which means that the logarithm of the observed time has a Gaussian distribution. Now that's a statement of this character, that a particular transformation, namely the log of the usual time measure, is Gaussian. That is, of course, a homomorphism from the order aspect of time into the order aspect of numbers. But it is not the measurement theoretic homomorphism at all. It's, since we're dealing with time being an interval scale, or time intervals are what we really are talking about. They're a ratio scale. They're extensive in character. The logarithm is not one of the acceptable transformations. Those are ratio scales and can only be transformed by multiplication by a positive constant. So in that situation, the mapping psi is not in this set of homomorphisms. Now, as you can see in that example, if I take a particular homomorphism, that is an additive measure of time, there does indeed exist a strictly increasing transformation that converts that additive form into the Gaussian random variable, namely, in the case I've just talked about, the logarithm. Now, notice that in these situations, the random variable psi may be viewed as an interval scale in the sense that only under linear transformations is the Gaussian property maintained. That's well known, and you're limited. If you're talking about a random variable that has a Gaussian representation, you're limited to interval scale transformations. Equally well, if I'm dealing with a scale, a measurement scale of sufficient restriction, I'll be dealing with an interval scale or even a ratio scale, as in that example mentioned, but let's talk about an interval scale. And so it's subject only to linear transformations if you're going to stay in the homomorphism group family of homomorphisms of the measurement structure. So both aspects of it are subject only to linear transformations, but it does not in any way follow from that the transformation that relates the two scales, the random variable and the measurement scale, it does not follow that that is a linear relation. In general, in these situations, it will be nonlinear. Now, I think that once this is clearly understood, then I don't think there's really any great problem in deciding whether or not you can use a Gaussian representation. It's simply the case that the random variable and the measurement scale need not, in general, be very tightly interlocked. Now, it may happen that one has theoretical reasons that permit you to derive a particular relation, for instance, a linear relationship between the two random variables, in which case, fine, you can use ordinary Gaussian statistics on the measurement scale directly if you have well-sustained reasons to think they're the same. But those reasons are not because you're dealing with two interval scales. That it does not follow that because two scales are each interval scales that they are necessarily tightly related to one another. And so it becomes really a problem for the scientist to establish independently of these kinds of uniqueness considerations what the connection is between his Gaussian random variable and the measurement variable.